Hello everyone, welcome back to my channel. In the last video I have shown you in detail how to calculate the magnetic anisotropy energy for nickel 100 monolayer, and in this video I will show you how to do the same calculation for iron 100 monolayer. Basically everything is the same. We first do a self-consistency calculation to calculate the ground state and the charge distribution, and we do a collinear calculation, which means that it's spin polarized, but the spin is along the z direction. And the second step is to do a non-self-consistency calculation. We start from the charge density and spin density from the last step, and then we do a non-collinear calculation, which means that the quantization axis is now arbitrary, and we add spin orbital coupling using a full relativistic ultra-soft pseudopotential, and spin orbital coupling results in the magnetic anisotropy energy that we want to calculate. And then we do step 2 with different spin angles. We make the spin along x and make the spin along z, yeah? And then we compare the total energy of the second step with different spin angles, and the difference is the magnetic anisotropy energy, yeah? Everything is the same as last time, except that we change the element to iron. And this is the first step, the input file, change it to iron, and the pseudopotential for iron, and you must use ultra-soft pseudopotential. And for those two values, we can actually read out from the pseudopotential. Let me show you. Put the pseudopotential here, and yeah, here you see that's 70,500, yeah. So we use 80,500 to make it safer. And the lattice parameter here, we use the bulk value. So basically we did one VC cell relaxation calculation for the bulk iron, which is a BCC lattice. In principle, you can also do a VC cell calculation using the same structure here. Yeah, you calculate the optimum lattice constant for monolayer of iron, and actually it will be different quite a lot. Just remember that in that case, you need to use cell dew free equals xy, so that it does not relax the vacuum spacing. And the way that we write the structure is different than nickel. Iron is a BCC lattice, so if you take one atomic plane, it is very natural to use the tetragonal lattice, and you only need one atom in one unit cell. So I can visualize that for you using X-Crystal. Yeah, you see that it is indeed a 2D square lattice. And then everything else is the same. And this is the input file for the second step, non-self-consistency calculation, the angle to the z-axis, and this is the angle of the projection of the spin onto the xy plane and the x-axis. So this means that the spin is pointed along the x-axis, and this line that we comment out here means that the spin is along the z-axis, yeah? Okay. And then the second calculation in the second step is that we comment out the first line, and then we actually calculate the second line here, which means that we calculate the z-axis situation, okay. And I just show you the output files. This is output file for x direction, and this is output file for the z direction. You just search EB, and also here, yeah, and we just copy those two. Here, z minus x. Since in this case there's only one atom per unit cell, we don't need to divide 2, so we just copy EV per atom, and the result is minus 0.48 milli electron volt per atom. And indeed, this is negative, which means that the EZ axis is out of plane, so that EZ is smaller than EX, and it is around 0.5 milli electron volt. There is a deviation here because you need to do a thorough convergence test over the K point and it cutoff, yeah, that I will not do here. I just want to show you how this calculation is done. So in the last two videos, I have shown you how to calculate the magnetic anisotropy energy of nickel monolayer and iron monolayer, and we have successfully reproduced the literature value as well as the correct EZ axis, yeah. And in these two examples, we use the lattice constant, that is the bulk value, but of course you can also relax the monolayer and get a very different lattice constant. However, the magnetic anisotropy would be quite similar. Thank you for watching. So if my video helped you somehow, I would really appreciate your like or subscribe to my channel, and I hope to see you next time.